Hello, everyone. Last time we were talking about the equation of hydrostatic equilibrium. And the equation is dPdr equals minus lowercase g, which we can express as g times m sub r over r squared times rho. And conceptually, what's going on here is that you have a balance of forces. You have gravitational forces pulling down on a blob of mass within the star, and you have buoyancy forces pushing up on it. I say buoyancy and not pressure to be a little bit more precise, because there are pressure forces from the bottom of the blob pushing up on it. There are pressure forces from the top of the blob pushing down on it. And the result of adding those two pressures together gives you the buoyancy force between the two. Presumably there's sideways pressures as well, but in spherical symmetry, those sideways pressures on any blob, that is in directions perpendicular to the radial direction, would all cancel with one another. And so that's what's going on with this hydrostatic equilibrium equation. And at the end of last class, we said, okay, well, let's just try to get some idea of what it is that this equation is telling us. And so we said typical values of dPdr would be the central pressure over the radius of the star in magnitude. And of course, dPdr is negative because as you go outward in the star, you will get to lower and lower pressures. We know that because everything on the right-hand side, other than the negative sign, is positive, or at least non-zero, or non-negative. The right-hand side, g m sub r over r squared. Remember what m sub r is. It's the mass enclosed inside a radius r. That quantity, we said at the very end of last class, was typically on the order of, and for m sub r, we just said, hey, we'll take the total mass and divide it by 2, right? It's somewhere between 0 and m, this m sub r is, so let's use m over 2. Likewise, lowercase r inside the star is somewhere between 0 and capital R. So for lowercase r, we just said r over 2. And the rho, the density, we used m over 4/3 pi r cubed, which would be the average density. And now today, this was actually new material right here. We're saying we are not going to worry ourselves with coefficients of order unity. We will do things like, say pi divided by 3 is 1, and 4 divided by 2 squared is 1, and 2 equals 1. We're not worried about constants right now. And so I say that this scales like gm squared over r to the 5th. And so we can put these two sides equal to one another, and we see that P sub c over r, but I'm going to bring the over r over to the right-hand side, is on the order of gm squared over r to the 4th. And you might ask, where did the minus sign go? There's a minus sign and there's a minus sign, right? And so when we put the negative thing on the left equal to the negative thing on the right, we can cancel the negatives and we're just left with positives. And this result is not surprising because if you think about what a pressure is, it's a force per unit area. And a force dimensionally, if all you have about your system is its mass, its radius, and it's gravitationally bound, so there's a capital G playing a role, the force is gm squared over r squared dimensionally. That's dimensionally a force. And we say pressure is a force per area, so we divide by an area. That's a 1 over area. And so, yeah, what do we get? We get, as expected, gm squared over r to the 4th. There's really no other thing that it could have scaled with. Now, if we go and we plug in values for m and r that correspond to our sun, then we can make an estimate of what the central pressure is for our sun. So for the sun, if we calculate gm solar squared over r solar to the 4th, we can plug in numbers, and this turns out to be about 10 to the 15 newtons per meter squared. And this is an underestimate. We've been very loose here with coefficients. We haven't solved the equation of hydrostatic equilibrium exactly by integrating. So this is the P at the center of the sun, our guess for it. And the actual pressure at the center of the sun is closer to 20 times larger. So I know we're off by a factor of 20. What's a factor of 20 among friends? But the idea here is not so much the exact value. We're one order of magnitude off, but the way that things scale. And so, for example, if I were to go to a star that had twice the mass of the sun and twice the radius of the sun, then I can guess how its central pressure would scale using the sun as a reference point. The m squared would be 4 times larger in the numerator for my new star, which is 2m solar. The denominator would be 16 times larger. So 4 times larger in the numerator, 16 times larger in the denominator. So overall, the pressure would be 1/4 what it was if I doubled both the mass and the radius. 1/4 of what it was in the sun. What questions or comments are there at this point?
Can we talk about the units?
Yeah, let's do it.
So we end up with newtons over an area. Is this because we're still dealing with the pressure? So it's the pressure acting at the surface area of the shell?
Right now we're talking about the pressure at the middle of the star if I put a subscript C on it. If I haven't put a subscript C on it, then it could be the pressure at any location within the star. And it doesn't have to be a shell. You can, if you like, think about some little blob somewhere in the middle. And it need not be shaped like a shell. And you can still locally talk about what the pressure is. And you might say, okay, well, what is the area then? What you need to do, perhaps, is imagine that you have some little parcel. And you could use the surface area of whatever parcel in your mind you imagine. And if, for example, this is being caused by ideal gas pressure, as we'll discuss about in a moment, particles are bouncing around. And every time they hit that boundary of your little parcel, they would impart a force to it. And the force per area would then be the pressure of that gas. So just like the pressure in this room or in the atmosphere of the Earth, everywhere can have a value at each location. We can say the same thing here, that you can have the pressure at each location within the star. Does that help or not?
It helps. So we just use the radius then as the position of where it is, and then everything else falls into place.
That's right. The lowercase r is the position of the little blob of fluid that you're considering. And so inside the star, lowercase r would be between 0 and capital R. And then, yeah, the idea here is that this pressure could be at any location, lowercase r. If I put a subscript C, then I'm thinking about lowercase r equal to 0. Other questions and comments or follow-ups?
I have a quick question.
Yeah, go ahead.
So what we're saying is this is for a small blob of fluid that's not at the center, because if r equals 0, then there would be 0 pressure?
No, it is true that when we write P, we are talking about a pressure anywhere.
Okay.
What I mean by P sub C is the pressure at r equal to 0. And
okay,
the pressure at the center is very much non-zero.
Yeah, that's the maximum pressure. What's 0 at the center then?
Okay, so what's 0 at the center are a couple things. But m sub r at m sub 0 is 0.
Yeah, that makes sense.
That'll imply that the local gravitational acceleration is going to be 0 at the center. So I'll put a g sub c on there.
Okay, but the pressure is maximum.
The pressure is maximum. The fact that you have a 0 right here at the center on the right-hand side proves to you that the pressure is a maximum at the center, or at least it proves that it's an extremum, because at the center, G equals 0, which implies dP dr equals 0, which implies that P is an extremum. And then there's only one more step to prove that it's a maximum and not a minimum. And that step is that, well, the pressure has got to be decreasing because the right-hand side's non-positive.
Okay, thank you. That makes sense.
Great. Yeah, thank you for asking questions. Other questions and comments? Okay, so for today you read about the equation of state. This is section 10.2 in your book. When someone says this term, equation of state, what they're referring to is pressure expressed as a function of other thermodynamic quantities. So it could be pressure. An equation of state gives pressure as a function of, say, density and temperature. And I'll write this as x sub I. You think about that I as being an index. It could be the numbers 1, 2, 3, up to however many species of material you're taking account of. Maybe x sub 1 is the abundance of hydrogen. X sub 2 is the abundance of helium. X sub 3 is the abundance of lithium, et cetera, et cetera. And so those x values are telling you what the gas is made up of, right? So hydrogen at a certain density and temperature might have a different pressure than helium at the same density and temperature, for example. And so in stars, the equation of state is often dominated by the ideal gas contribution. We'll talk about other forms of pressure that contribute to the equation of state. Radiation contributes, electron degeneracy pressure contributes, neutron degeneracy pressure can contribute. But in most stars, ideal gas pressure is the most important contribution. And so that's where we're going to start. And you may remember way back when you might have had a chemistry course in high school where you first learned the ideal gas equation of state. Does anybody want to shout out the equation that they were taught in high school for chemistry for the ideal gas law? Maybe you still remember it.
PV equals nRT.
Oh yeah, that's it. PV equals nRT. And so since you've seen that before, we'll use that as our starting point. It's worth pointing out that here, this N is referring to the number of moles. And that's going to be a different quantity than what an astronomer will refer to as N. So later on, we'll write down another N, the number density, and that's different than the number of moles. So we'll just keep that in mind. We'll reuse that notation later. Well, what we can do is, remember the number of moles is the number of things you have divided by Avogadro's constant. 6.02 times 10 to the 23. So here, Na is 6.02 times 10 to the 23. If you have that many tennis balls, then you have a mole of tennis balls, for example. And so, fine. The next thing that I'm going to do is I'm going to redefine the gas constant, capital R. So capital R has some value. It's a constant of nature, 8.31 joules per mole per Kelvin. And I'll write out Kelvin so we don't confuse it with the Boltzmann constant. And this R over N is the Boltzmann constant. This is N times K times T. What I'm trying to do here is start to get closer to write this to the way an astronomer will write it in a more convenient way, as you'll see. The point here is that you've probably, at some point in the past of your life, if you had a chemistry course, you've probably seen the gas constant before. And you probably have now, since you've taken physics classes, seen the Boltzmann constant before. You've seen it in this class. But you may not have appreciated that those two things are linked together very simply by the Avogadro's constant, N sub A. In fact, you can see that K is just R over N sub A. And if you were to run to your calculator and take that value of R and take that value of A and divide them, you would get the value of K that you've probably looked up on the inside front cover of your textbook before, 1.38 times 10 to the minus 23 joules per Kelvin. All right, so this is cool. PV equals NKT. And that's good in high school chemistry when you're dealing with things like, you know, you have a tube or a chamber or something with a constant volume, or maybe even the volume's changing, but throughout that volume, everything is uniform, right? Everywhere within this volume in high school chemistry, the pressure is the same, the temperature is the same. And so it, you know, makes sense to use equations like this one, where you just have a value of pressure and a value of temperature because it's the same everywhere in the volume. Now, in a star, it's more complicated than that because as you move about in a star, the pressure at the center of the star is going to be different than the pressure outward, and the temperature at the center is different than the temperature over here. And what do we mean by the volume? If you take the volume of the whole star, well, the pressure is not uniform within that volume. The temperature is not uniform within that volume. So if you mean by the volume of the whole star, what temperature and pressure do you use? It's not well defined. And so what we need to do is we need to make this a localized equation, make this into an equation that works at a small scale. And so what we're going to do to make that happen is we're going to divide both sides of the equation by this volume V. And so imagine you're somewhere within the star and you take a little parcel of gas. It's small compared to the star as a whole, but it's large enough to contain many of your constituent particles within it. And if we've divided both sides by V, we get P equals N over V KT. So inside that little parcel of volume V, there are N particles. And what's the name we give to N over V?
Number density.
Yeah, that's the number density. That's the definition of number density. So here we'll write NKT, and now the N will be the N as in the rest of this course, no longer the number of moles. That's the number density, right? Hashtag density. You've seen this before, but let me remind you how the number density is related to mass density. The number density N will equal the mass density rho divided by the average mass of a particle. If you take the mass per volume, that's the numerator, and divide it by the mass per thing, you get the number of things per volume, and that's exactly what number density means. And you can think about this dimensionally. On the left, we have 1 over a volume. On the right, we have a mass over a volume divided by a mass, so it's also overall a 1 over a volume. And so I will say N is equal to rho over m bar. That bar over top of m just means that we're taking the average particle mass. And of course, you could always rearrange that. This is useful if you know rho and m bar, and you want to know n. But if you know n and m bar and you want to know rho, well, of course, rho is n times m bar. We'll define one more quantity. And this quantity is very important in stellar evolution. When you're modeling stars, you'll see this all over the place. It's called the mean molecular mass. And we'll spend some time today calculating. It's actually more commonly known and called in your book the mean molecular weight, so I'll stick with that. The mean molecular weight, mu, is the average mass of a particle divided by a proton mass. So it's a bad name, mean molecular weight, because it's not a weight. It's not even a mass. It's dimensionless, because it's the mass of a particle divided by the mass of a proton. And so if you had, I'm going to ask you a trick question. No, I won't ask you a trick question. Let's just say I had a box of protons. What is the mean molecular weight?
1.
1, yeah. Your average particle mass is a proton mass divided by proton mass. Mean molecular mass or weight is 1. What if I had a box of protons with an equal number of a box of, in the same box, with an equal number of free electrons? So for every 1 proton, there's 1 electron. What's a good approximation or first guess at what the mean molecular weight is?
1.
Not 1 any longer.
1/2.
It's 1/2, right? Because for every, the electron weighs 1/2000th approximately the mass of a proton. So we'll pretend the electron didn't have a mass so that we can do this easily in our heads. And so for every proton, there's an electron. So the average mass of something is the total mass, which is the mass of the proton, divided by 2. And so mu would be 1/2 for that case. And you can imagine inside stars, as you start to add helium and metals to the mix, and you ask yourself, well, are these elements ionized or not ionized? In other words, are the electrons on the atoms? In which case, you still count them as one object. If an electron is on the atom, it's just one thing. But if you rip it off, you ionize the atom, now it's 2 things. So depending on what the composition is and whether or not the that composition, those elements, those species are ionized, you'll get different values for this mu.
Dr. Lombardi, I have a question.
Yeah.
When you're determining what materials are in it, is that where we use the light spectra that we talked about in previous chapters? That way we can figure out what types of elements are there and in the composition?
That would play a role. That's a related question. So certainly if you change the abundance that you're considering, then you're going to change the absorption lines or emission lines that you have, right? Mostly absorption lines that you have coming from a star. And separately, if you change the abundances, you would change this mean molecular weight. Right now, we're not in the process of talking about the light. We're talking about the pressure that is pushed outward by a little parcel of gas. But of course, both of these things would depend on the composition. Does that help?
Yeah, so how do we figure out what the composition is?
What you brought up about looking at the spectra and being able to see where the absorption lines are, that would tell you or help you to determine what the composition is. And then once you know the composition, you could use that to calculate a mean molecular weight, and then you could use that to model your star.
Thank you, Dr. Lombardi.
Yeah, thank you.
I have a quick question as well.
Yeah.
I'm just wondering about how rotation of a star would affect or complicate the pressure calculation.
It does complicate it. And you can solve that in an approximation where you have, if you treat the star as each shell rigidly rotating, if it's rotating slow enough, you can write down the equations as an expansion in the angular velocity omega. But for fast enough rotations, it becomes a nonlinear problem that the only way you can solve it is numerically. And there are certainly stellar evolution codes that exist. The Yale rotating evolution code was one of the first, which treats stars that are rotating. Most evolution codes that you use, at least in most applications, are for non-rotating stars. However, there are a lot of people out there. I mean, you can go to conferences that are about rapidly rotating stars, for example. And then, yes, it'll be more complicated than this. Basically, one of the ways you can think about it is to a crude approximation. The effect that rotation has is to decrease that G right there. because you have a centrifugal acceleration outward, this fictitious force due to the rotation. And so you don't need to have quite as much buoyancy force to counteract the gravitational pull inward. The effective value of gravitational acceleration at any location is a little less than it would be if there were no rotation.
Okay.
Other questions and comments? So if you look at the top of the board and this expression for n, we can combine these two things, right? P is equal to, for n, we write rho over m bar. And if we like, for m bar, we could write that as mu times the mass of a proton. And this is our final expression for the ideal gas. And this is nicer than writing it in terms of V and the V, the volume of the gas, right? And N, the number of particles, because this is a locally valid expression. You can go to any location in the star and you can talk about what is the temperature there? What is the density there? What is the mean molecular weight there, right? These are all things that you can plug in values for now at any location you like, and you can get the pressure there. Now, it's worth adding the subscript here, gas, at this point, because there's going to be other contributions to the pressure, right? There could be contributions to the pressure from photons, radiation, and other things. And so I didn't want to have to keep writing gas, gas, gas all the way down. But now in the final line, I'll remind us that this is the pressure due to a gas, an ideal gas in particular. What about other contributions to the equation of state? I said that in most cases, the ideal gas was the most important pressure. For many stars, the next most important thing is the radiation pressure. And I did actually have you read the relevant page before break. We're not going to derive it here, but rather I'll just state for you that P rad, the radiation pressure, is 1/3 A T to the 4th. You've seen this T to the 4th come up a lot. It comes up a lot when you talk about light. You've seen sigma T to the 4th is the flux of light. In your reading, you may or may not remember the energy density of radiation scales like T to the 4th. So what do I mean by that? You have inside of your star, you know, photons bouncing around. And the hotter the gas is, the more energy there is going to be in these photons. They're going to be higher energy photons. There are going to be more of them. And that energy density scales like T to the 4th. The pressure that the photons push out with also scales like T to the 4th. Photons carry momentum. And, you know, if a photon comes and hits your skin and is absorbed by it, it transfers so much momentum. And if there's many doing it, then there's so much momentum per time, which is a force. And then you could calculate per area on your hand, and you get the pressure due to the photons. A here is the radiation constant, and you can look up its value. It's a constant of nature. It's actually related to sigma, the Stefan-Boltzmann constant. It's 4 sigma over the speed of light, and it's numerically 7.6 times 10 to the minus 16 newtons per meter squared per Kelvin to the 4th. And of course, in SI, it had to have been those units, because when we multiply it by a temperature to the 4th, we need to get a pressure, newtons per meter squared. You might wonder, okay, well, let's take the sun, for example. How good of an approximation would it be to simply use the ideal gas expression for the pressure everywhere? And so let's find out by doing a simple calculation. In the center of the sun, the central density is about 162 grams per cubic centimeter. So converting that to SI, that's 1.62 times 10 to the 5 kilogram per meter cubed. The central temperature of the sun is between 15 and 16 million Kelvin. So we'll say that it's 15.7 times 10 to the 6 Kelvin. And the mean molecular weight in the center of the sun, you see, is 0.85. And so if we like, using these values, we can calculate the gas pressure at the center of the sun. That's at rho kT over mu mp. You just have to plug in values. And this turns out to be, well, I already told you it was a little more than 2. It turns out to be a little more than. It's about 2 times 10 to the 16 newtons per meter squared. If you calculate the radiation pressure in the center of the sun, that's just 1/3 AT to the 4th. So you just plug in. Doesn't matter what the density is. It only matters what the temperature is. And you get about 1.5 times 10 to the 13 newtons per meter squared. So the radiation pressure is more than 1,000 times less important than the ideal gas pressure here. Comments or questions on this?
Does radiation pressure dominate over gas pressure in the center of any stars?
There are stars, like one you'll test on your homework, where P-rad starts to become more important because it gets closer to P-gas. It is honestly hard to find a star where P-rad is going to be as large as P-gas. Maybe if you search long enough and think about enough different stars, you could probably find a case. But for main sequence stars, at least, and this meant something that the Hertzsprung-Russell diagram. For main sequence stars, at least, even though the radiation pressure becomes more important as you go up to the higher mass stars, it still is always not quite as important as the ideal gas pressure.
Okay, thank you.
Other questions and comments?
I have a question about how this plays out in stellar remnants. What would these pressures be in something like a white dwarf or a neutron star?
Right. So wonderful question. And neither of these are important in a white dwarf. Right. It turns out to be electron degeneracy pressure, which is the most important thing in a white dwarf. And in a neutron star, they have very complicated equations of state. The first approximation that you make at a neutron star equation of state is neutron degeneracy pressure. So again, neither of these. But then there are other complications, and people argue about what the correct neutron star equation of state is. But these are now small effects. So that's a good point. And we're not yet at the stage where we're going to be writing down the equation of state for compact objects.
Thank you.
Thank you. Other questions and comments? What I'd like to do here in the final 10 or so minutes is to derive an expression that connects the mean molecular mass, mu, to the abundances. Often astronomers use capital X and capital Y and capital Z to represent the mass abundances of hydrogen and helium and everything other than those, respectively. So what capital X is the fractional abundance by mass of hydrogen. So fractional abundance by mass, I won't write it down, but you do need to remember it's by mass, not by number, of hydrogen. And Y is the fractional abundance of helium. And Z is the fractional abundance of metals. And to an astronomer, a metal is anything heavier than helium on the periodic table. So lithium, beryllium, carbon, nitrogen, oxygen, any of these things, they're all metals. It doesn't matter if they conduct electricity well or not. It's a metal if it's not hydrogen or helium. And now what do I mean by a fractional abundance? What I mean is that x plus y plus z has to equal 1, right? 100% of your stuff is either hydrogen or helium or a metal. And so what I want to do is take a box and imagine that there is a mixture of species within this box. And the numbers or the variables x and y and z, those will specify how much of each of these species I have. And in what follows, m is going to represent the total mass in the box. And m sub I is going to represent the mass of species I. Oh, and by the way, the answer to today's reading quiz will be my TA is a cat. My TA is a cat. That is the answer to today's reading quiz. Back to the lecture. Mass of species I in the box. And so if I is equal to hydrogen, we're talking about the mass of hydrogen. If I is helium, then we're talking about the mass of helium, so on and so forth. My goal is to calculate mu. And I will make one more stipulation on this. I will say that the gas is fully ionized. So for every proton there is in a box, there's a free electron in the box as well. So if I want to calculate mu, remember what mu is. It's the average mass of the things in the box divided by the mass of a proton. So I need to start trying to figure out how am I going to calculate the average mass of a thing in the box. Well, if I take the total mass and I divide by the total number of things, that would be the average mass of the things in the box. So I need to start thinking about how am I going to calculate the total number of things? Well, the number of hydrogens is the mass of hydrogen divided by m sub p, the mass of one hydrogen. Remember, a proton is a hydrogen nucleus. And the mass of hydrogen, m sub h, is x times the total mass. So for example, if x were 0.4, 40% of the total mass is in hydrogen. When I write down the expression for n sub he, we'll see how things change. It's still the mass of he, or the mass of that species in the numerator, but now I need to divide by the mass of a single helium nucleus, m sub he. If I take the total mass divided by the mass per helium nucleus, total mass in helium divided by mass per helium nucleus, then I would get the number of them. Now the numerator I could write as y times the total mass. And approximately, how many proton masses is a helium nucleus?
2.
Okay, you're close. You realize correctly that there are 2 protons in a helium nucleus. However, there are also 2 neutrons in the helium nucleus that weigh almost the same as the protons. And so why don't you modify your answer?
4.
4. Right. It's 4 times the mass of a proton. And then finally, well, not quite finally, because we have to think about electrons. The metals are the mass of metals divided by the mass of a metal nucleus. And so the numerator is Z times capital M, and the denominator is A times M sub P, where A is the atomic mass number. And yes, it's true that you could have a mixture of many different metals. You could have oxygen and nitrogen and carbon among many other things. a typical value of A is about 16. Corresponding to oxygen. And so that is an average mass number of the metals. I say corresponding to oxygen because remember, oxygen has 8 protons and 8 neutrons in it, 16 nucleons. And you don't have to be too ultra precise here because the metal composition is usually no more than about 2% in a star. And so it in itself is a small correction. So we said that this gas is fully ionized. And so if we want to take into account the number of things, we also need to take into account the number of electrons. It's fully ionized, so the number of electrons is the number of hydrogens plus the number of heliums plus the number of metals. Oh, and I made a mistake. I'm trying to go too fast here because I know I've got to wrap up. If you have a helium nucleus, how many electrons are associated with each one helium nucleus?
2.
Yeah, because there are 2 protons, there will be 2 electrons as well. And then likewise, in general, it's approximately the case that the heavier elements have the same number of protons and neutrons in them. So as an approximation, we can say that each metal nucleus has A over 2 protons in it, and therefore there would correspondingly be A over 2 electrons for each one metal nucleus that we have. Now I only have a few more seconds, and I'm not going to have enough time to write out the math in its gory detail. However, at this point, it's all just algebra. You can figure out that the mass per particle is the total mass divided by the total number of things. And you see how each of these capital N's have a capital M in the expression for it? And therefore N sub E would even have a capital M in its expression. So the capital M in the numerator here would cancel with the capital M's in the denominator down there. And so it doesn't really matter how big of a box you had, what the total mass within that box is, when you take this ratio. And so I'll write down the final result here. It is that mu, which is equal to, remember, m over the mass of a proton, is equal to 1 over 2x plus 3/4 y plus 1/2 z. And I have made an approximation in that last step there. I've used that 1 plus a over 2 is approximately equal to a over 2. In other words, I could have been a little bit more precise, but I wanted the a's here to cancel away. And if you don't make that approximation, this z term is a little more complicated than that. But because z itself is already small, we don't really need to be any more precise than this. And so this is how you calculate mean molecular weight, or mass, from x and y and z. And let me remind you that this is for a fully ionized gas. If it weren't fully ionized, if it were, say, neutral, then you wouldn't have this Ne contribution. And you wouldn't be dividing by a plus Ne in the denominator there, wouldn't have that term in it, because the electrons would be on the nuclei and they would count together as one. All right, so the last thing I'll say is that this is equation 10.16 in your text. So if you want to connect it to the reading you've been doing, you can look there. Any final comment or question?
Yeah, Dr. Lombardi, so on average the stars aren't going to be either fully ionized or neutral?
On average, they're going to be fully ionized.
Really?
Yeah, even all the way out to the photosphere, you have full ionization. Now it's true in the atmospheres of stars, which is where light is coming from, then you can start to have partial ionizations. And you can certainly see people work on this, and there's plots that you can find, as a function of position within the atmosphere, what the ionization fraction is. So I'm not trying to claim that the star is fully ionized everywhere. But if it's the interior of the star you care about, and you're not worried so much about the light coming from it, that the atmosphere is just fluff to you, and you care about when stars collide, for example, where does the mass go and so on, then it's a wonderful approximation in almost all cases to say that it's fully ionized. So for hydrogen, for example, I forget exactly how many thousands of Kelvin I want to say, but somewhere on the order of 10,000 Kelvin. If it's, or maybe 5 to 10,000 Kelvin. I don't know the number off the top of my head. But at temperatures hotter than that, it's fully ionized. So remember, the temperature of the sun goes all the way to 15 million in the core. So it's only when you start to get at and outside of the photosphere that you need to worry about partial ionization.
Cool. The other thing I had a question about was the metals in stars. Where do the metals come from?
Where those metals come from is previous generations of stars dying and ejecting their gases out into space. And so for stars like the sun that formed out of gas clouds that had been polluted by previous generations of stars, there's almost 2% metals in them. But if you look back in the early episodes of the universe, when stars were just forming for the first time, like in globular clusters, some of them are very old stars, and their metal abundances are usually around 0.1%, so maybe 20 times smaller than what it is in the sun.
Okay, that was it. Thank you.
Okay, that's it for today. Stay safe, take care, and good seeing you.